Hey, hey. So we're going to do a quick little discussion on average atomic mass, calculating average atomic mass, and calculating percent abundance when you're given the mass of the isotopes, which is new. Okay, I guess maybe it probably is. So let me go here, and no PowerPoint right now. Back to my little camera board here. So we're going to talk about average atomic mass. And this is the mass represented on the periodic table. Okay, so if they say mass number, they're talking about an actual particular atom or isotope. If they say average atomic mass, they're talking about the average of all the isotopes of a given element and their percent abundance. So if you see atomic mass, right, it's just referencing maybe the mass of that one atom. Like this chlorine atom weighs 35, some chlorine atoms weigh 37. The other atomic mass of this chlorine is 35. The atomic mass of this chlorine is 37. However, as we see on the periodic table, the average atomic mass is 35.45. That is atomic mass units. You can't use grams because grams is not appropriate for something that small. So they've made their own unit for these atoms, okay? So what we're gonna look at is how to get these numbers. How to get the number here, which is the number you see on the periodic table. You should remember this. And then those of you that are here, we're also going to look at how to determine the percent abundance when you're given the masses. Okay, so let's start first. For those of you that may not remember the basics, I'm going to make this up. Let's say that we have an element X that has a mass of 49.47, and he is 60% abundant. Element X, same element, it's an isotope of element X. What is an isotope? Same number of protons, different number of neutrons. So we're going to see varying mass values here. Let's make this a 9.7, guys. 49.9, so we make it closer to a whole number. No reason. Let's say that we've got another one. It's got to be somewhere around here. I mean, I could go down to 47 if I wanted to. 47.01. How about that? We'll make him 10% abundant. So I got 30 more percent to go. Let's go ahead and finish that out with this guy here. We'll make him weigh maybe 49.01. 60 plus 10 is 70, so he'll be the remaining 30%. So element X has 3 naturally occurring isotopes. The first one weighs around 50 AMU, 47 AMU, 49 AMU. We see that he is the most abundant, so he's going to carry the most weight. All right. What are we going to do? We're going to take 49.97. We're going to multiply it by 60. And we're going to divide that by 100 either now or later. We're going to take 47.01. We're going to multiply it by 10. And we're going to divide that by 100 either now or later. We're going to take 49.01. We're going to multiply it by 30. And we're going to divide that by 100 either now or later. We're going to get these values. We're going to add them up. And we're going to have our average atomic mass. Now, it's so easy, right? I mean, that's it. All we do now is throw these numbers in the calculator. But I'm going to tell you, notoriously, every single year, students take these values, they add them up, they divide it by 3, they give me that as their answer, and I just laugh Those of you that watch me grade papers, that's when I am just laughing. Now I'm going to say times 0.6 because I know that this divided by 100 is 0.6. Close parentheses equals. Now I'm going to divide, I'm going to add to that this. I'm teaching you how to do this more quickly. 47.01 times, that's going to be 0.1. I will add to that 49.01 times 0.3 equals, pretty much as we predicted, something very close to this number. Always check to make sure that your answers make sense. 49.39. Okay. Always use a label. And that's how you calculate average atomic mass. If there were 10 isotopes, I would do this 10 times. All right, I just did it all in my computer at once by using, or I mean calculator rather, by using parentheses. Let's look at one more example of a different problem, which you are expected to know how to solve. And that would be a situation where you have to calculate those percentages. And it's just a more mathematically based problem. And I'm going to have another fake element here. Okay, this time let's have element Z. And we'll say that he weighs, what's a good number? Let's have him weigh 78. Man, we should have done 2020, huh? Let's keep it simple as 78. All right, keep our math simple. And we'll have another naturally occurring isotope for this fake element Z. I'll make him weigh 75. All right. And I know either because it was given to me, which it's going to be now, or because this is a real element, so I find his average atomic mass from the periodic table, right? So if this was a real element, I would look at the periodic table to determine the average atomic mass. This is a fake element, so I am making up a number, okay? Should we put some things behind these? Let's do it. Let's do it. Let's go ahead and do this. Just for the sakes of it, okay? And this is all fake. Otherwise, I would be given this. I would be given this. I would look at the periodic table to find this based off of the element here. Okay. I wish I had more room. What I'm going to do is I'm going to say, well, 7, it's just kind of plugging in what we did a minute ago and solving for a different variable. Now you will only, I'm going to let my AMU go. I know I'm breaking the rules. You will only do this if you have 2 isotopes, and you'll see why in a minute. So I'm going to say that this isotope is X% abundant. Actually, this is going to be this is going to be the decimal version. I'll show you why in a minute. And if I add that to this isotope's mass, and like I said, you can only have 2 isotopes to solve this problem. I know that his abundance will be 1 minus X, because X in its decimal form and this X in its decimal form must add up to 1. When I solve for X, it will be the abundance in the decimal form of this isotope. And then I will subtract it from 1 to get the abundance in decimal form of this isotope. I will then multiply them by 100 to get the final percent abundance. If I wanted to, I could go ahead and make this a 100, but I don't want to. Okay, you can. I don't care. I don't want to. I'm just going to do very small or very basic, slow algebra. Simplification, right? Let's distribute this. Okay, now I need to just start simplifying this. So what I'm going to do is I'm going to subtract this guy from both sides of my equation. Right, you guys are better at math than I am. That's going to give me 0, right? So 77.20, clear, 77.20 minus 575.29 equals, and that gives me a 1.91. So now I know that 1.91 equals, this is going to be gone. So let's go ahead and simplify this by subtracting 75.29 here and figuring out how many x's we have. 75.29 minus, oops, clear. 78.15 minus 75.29 equals 2.86. Oh my goodness. Let's fix that. 1.91 is now equal to 2.86x. Okay, I'm now going to solve for x. How about for you algebraically challenged people? We'll divide both sides by 2.86. 1.91 divided by 2.86 equals, and it looks like this is 0.668. Let's go 7878. All right, that's what x equals. So remember x, this is x. X is telling us the percent abundance of this. That's what the question is asking for. Percent abundance of each isotope equals what? Right. So if 78.15, right? If isotope Z 0.15 has an x that is equal to 0.6678, and we multiply that by 100 to get a percentage, we'll see that 66.78% of the isotopes of element X come in this form. And then 1 minus, right? We need to solve for this guy, 0.6678. You can almost do that in your head. It's going to be, yeah, 0.3322 times 100 gives me element Z dash 75.29 dash has an abundance of 33.22%. And we have, oh my goodness gracious, we have solved that problem. Okay. And that's it. That, my friends, is it. So I'm going to go like this, and I'm going to say goodbye. All right.